The first question I want to ask is, what exactly is an orbit? I mean, we all know what they are. We live in a very modern society, and we know that we've got GPS satellites in orbit. We've got the space shuttle or other types of rockets which will be in orbit. There's the International Space Station, all kinds of space debris for sure, lots of space junk. But what is an orbit? Well, before orbits became a part of our everyday understanding of the universe, Newton thought about this. And I want to go through this little thought experiment with you very quickly. So basically, here's the situation. We have a hill and a level section of ground on each end of the hill. And if you're standing up here and you throw a stone, if you just throw it, kind of weakly, the stone's going to fall to the ground and it's going to form a parabolic path and it's not going to go very far. If I throw it horizontally with a much greater speed, then it's going to go further, but eventually it's going to fall back to the ground. And if I throw it with an even greater speed, it might actually land on the hill, or better yet, go beyond the hill and land on the ground beneath. And that's the idea behind orbits. So let's take another look at this, but let's zoom out far enough that we can actually look at the entire Earth, and you're standing on top of the highest mountain, which I guess would be Mount Everest. Okay, so here we are. You're standing on the top of Mount Everest, and you're going to throw this stone. Now you've got a really strong arm, and so you can throw it just as fast as you need to. And we're so high from the surface of the Earth that we can totally ignore air resistance. And so what happens, you throw the stone really, really hard, and it lands here. And then you throw the stone even harder, and it lands here. If you throw it even harder than that, then it might go around something like this. And then it lands here. And if you throw it even harder than that, I think you can see where this is starting to go now. Eventually, it's going to come right back around to you. So what was the mechanism which caused these stones to fall to the earth, but then when we zoomed out, they fell to the earth, but they started to actually wrap around the earth? The actual mechanism here was gravity. And gravity is what's going to keep a satellite in orbit. So what's actually happening here? Well, orbital motion is kind of like projectile motion, but the forward velocity is so great that the Earth curves out from underneath the object by the time the object would have struck the Earth. In other words, it's kind of like falling towards the Earth, but missing. Okay, now that's not a very scientific explanation, but that's basically what's happening. You're falling towards the Earth, but you keep missing it. Okay, and that's because you have a very, very high forward velocity. Now, there are actually some specific numbers here which are important. If you take a look at the Earth from a zoomed out position, not as far as this where we can see the entire Earth, but just that we can see some of the curvature of the Earth, then what we see is this, that if you go out 8 kilometers, the Earth will drop by 4.9 meters. So this is 8,000 meters straight out, and this is 4.9 meters straight down. So basically what we're suggesting here is that if you can make something travel near the surface of the Earth at 8 kilometers per second, which is approximately 5 miles per second, then the object will be in an orbit. Now, if you're doing it, from, say, standing on the surface of the Earth, there's going to be all kinds of stuff that gets in the way, even if we do ignore air resistance. But if you get further up and you don't have any other objects in the way, then you don't have to worry about it. Okay, so let's talk about orbital velocity for circular orbits, because as of right now, there's absolutely no way we could do anything with elliptical orbits. We just don't understand enough physics at this point in time. However, we can easily understand orbital velocity as long as we stick to circular orbits, because this is a unit on circular motion, and that's what allows us to be able to do this. But there will be other methods and techniques that we can use later on in the year to more fully analyze orbits, even if they're not circular orbits. The circular orbit is really a special case of orbit, just like we see with frictionless bank curves. And, basically a circular orbit is exceptional in the natural world. Now, in the man-made world, whenever we get to place things in orbit, we can put them into circular orbits, and in fact, we do all the time. Most artificial satellites are going to be in a circular orbit, not an elliptical orbit. So we're talking about GPS satellites, communication satellites, the space station. So just like we had with frictionless bank curves, we came up with a specific equation, and that equation was used to establish a critical value for understanding a more complex situation. The same is going to hold true when it comes to circular orbits. That yes, the circular orbit is a special case if we're looking at natural orbits, or orbits for things that are occurring naturally. So we're talking about planets going around the sun, moon going around planets, things like that. Captured asteroids, for example. So in nature, it's going to end up being exceptional. But understanding the circular orbit, or we get this critical value, a special velocity. There's only one speed an object can have whenever it's going to be in a circular orbit. If it's going too fast, it's going to form an elliptical orbit, and if it's going too slow, it's going to form an elliptical orbit. And I'm going to draw a picture of that in just a moment. What I've written here is that if the velocity of a satellite is greater than the orbital velocity that we calculate for a circular orbit, then the satellite is going to make a large ellipse. And I'll show you what that means here in a moment. If the velocity of our satellite is less than the critical value for the orbital velocity of a circular orbit, then the satellite is going to form a small ellipse. So let's start first by drawing the Earth. And then we're going to put around the Earth the circular orbit. And then we're going to look at what happens when you're going too fast. We're going to look at number 1 here. Okay. So if you're going too fast for this circular orbit, then you're going to form an elliptical path which looks something like this. Okay? And if you are going too slow, right, that's this one. If you're going too slow, then you're going to form an elliptical path that looks like this. You're going to zip around the far side of the Earth and then come back out. So both of these paths are ellipses. It's just one, at this point in space, if you're going too slow, that becomes the furthest point from the central body. And if you're going too fast to form that circular orbit, that becomes the closest point to the central body. Also, keep in mind some of the symmetries that we were able to glean from Kepler's second law. And that was, out here, we're going to be far from the central body, so the satellite is moving slow. And then here, the satellite is moving fast because it's closer to the central body. where this would be a constant speed, the white line for the circular orbit. That's going to be a constant speed. Now, let's take a quick look at how we determine what the orbital velocity is. So the first thing you want to do is draw an FBD. And I'm going to draw more of a diagram here, which will have the FBD on it. But again, we're going to have the Earth right here. So here's the Earth. And then we have the circular orbit of the satellite around the Earth. And we're going to place our satellite right here. So maybe this is Sputnik or something like that. And Sputnik had these antennas that came out of the back as it moved around the Earth in that direction. Now, in terms of our FBD, there's only one force which is acting on the satellite, and that's going to be the force of gravity. And we know this must be the case because there's nothing touching the satellite. So there's only one possible force that we can have, and that's the force of gravity, the attraction of the Earth for the satellite and the satellite for the Earth. And so now to finish getting orbital velocity, we just set this up like we do any other force problem. We start by writing F net is equal to ma. We understand that the acceleration is going to be centripetal, and we know that a is going to be equal to v squared over r, and that for F net, we're just going to write Fg, and Fg is going to be universal gravitation. And the way we know that is that we're very far from the surface of the Earth. Anytime you're outside the limits of where a human can survive, you must consider universal gravitation. Now, if you're on something like, say, the top of Mount Everest, or even a little higher than that, in most problems you can ignore universal gravitation and just use mg for the weight, or the force of gravity. But there's a few special cases of problems where you actually would have to use universal gravitation. But absolutely for certain, once you get to orbits, you have to use universal gravitation. So Fg here is just going to be equal to gm of the Earth times the satellite over r squared. And so we write g, mass of the Earth, mass of the satellite over r squared is equal to the mass of the satellite times v squared over r. Now remember that r is going to be the distance from the center of the Earth out to the orbit. So that's going to be r. Now you should notice that the mass of the satellite cancels out, and so does one of the r's. And quite frankly, it should make sense to you. It should almost be intuitive that the mass of the satellite is going to cancel. Because one of the things we know to be true is that on the surface of the Earth, at least, when we have free fall, it's independent of the mass. Another way you know this to be true, or should know this to be true, is when you watch astronauts on a spacewalk. There's plenty of videos on the internet of astronauts being outside of the space shuttle or the space station. And the fact that they're not tethered to the space shuttle or space station in any meaningful way, is direct evidence that the mass of the person doesn't matter. Because there's a huge difference between the space shuttle and a person in terms of mass. And yet they stay exactly beside the space shuttle at all times. So you've got the visual evidence through video, and then we've got experience with acceleration near the surface of the Earth that tells us it makes complete sense that the mass of the satellite does not affect the orbit itself. Now basically here we're done. I'm just going to rearrange this so that v is on the left side, and we get v squared is equal to g times the mass of the central body. In this case, it's the Earth over r. Now, we rewrite this as v orb. It's pretty much always referred to as orbital velocity. And orbital velocity is the critical value. M is going to be the mass of the central body. And of course, R is going to be the distance from the center of the central body. Now keep in mind that the mass is in kilograms, R is in meters. That way 6.67 times 10 to the minus 11 works for G. Otherwise, you're going to have to redo your constant. And therefore, the velocity that we get from this is going to be in meters per second.